Hello, this is Mrs. Decker, and this is Objective 1D. I can describe the differences between exothermic and endothermic energy changes. Before we get started with today's lesson, we want to go back and do a quick warm-up of 1C, converting temperatures and converting units of energy. So the first problem says convert 48.5 degrees Celsius to Kelvin. So in order to do that, we are going to add 273. So you get 321.5 Kelvin. The second problem says convert 31 kilojoules to calories. So write your given information and set up your T-chart. So for this, you need to know that in 1 kilojoule, there are 1,000 joules. And remember, you need to remember that conversion. I will not give it to you. And then we use our conversion factor of 4.184 joules is equal to 1 calorie. So when you do 31 times 1,000 divided by 4.184, your answer should be 7,410 joules. So now let's get into today's lesson talking about exothermic reactions. In an exothermic reaction, it has certain characteristics that let you know that it's exothermic. Energy as heat is released into its surroundings, so it will make its surroundings feel hot to the observer or warm. When we're writing an equation for an exothermic reaction, we write heat as a product since heat is released. It could also be written as plus energy, or it could also be written as a specific amount of energy, like plus 30 kilojoules. So anytime you see any of those things written on the product side of the equation, that tells you that this is an exothermic reaction. Also, delta H is negative for an exothermic reaction, and delta H is the energy that flows as heat. So heat is flowing out of the system, that makes it negative. So now we have 3 pictures that are examples of exothermic reactions, and we want to look for clues that tell us that these are exothermic reactions. So for picture number 1, we have a campfire. The fact that we have burning fire, that burning is a clue that this is an exothermic reaction. Anytime you have burning or explosions, that's an exothermic reaction. So the same thing with number 2, firing a gun, you get a little mini explosion as the gun fires. So that is a clue that this is an exothermic reaction. So now number 3 is one commonly thought of as an endothermic reaction because when you hold ice in your hand, it feels cold, and generally exothermic reactions make the surroundings feel warmer. However, when you are going from liquid water to ice water, heat has to come out of the water in order for it to freeze. So this is an exothermic reaction. So anytime anything is freezing, that's a sign that it's an exothermic reaction. Now let's take a look at endothermic reactions. In an endothermic reaction, energy in the form of heat is absorbed by the system from the surroundings. So in general, it's going to make the system feel cold to the observer. So when we're writing an equation for an endothermic reaction, energy or heat or kilojoules is going to be written as a product because that is going to be used up and absorbed by the reaction. Our delta H for an endothermic reaction is positive because, again, heat is flowing into the system. Heat is being used up. So here are a couple of examples of endothermic reactions, and we want to look for which clues tell us that these are endothermic reactions that are happening. So for our first example, the plant, for a plant to grow, it must take energy into itself. So anytime it's taking energy in, that's an endothermic reaction. Anytime something is growing, it needs to take energy in. So growing is a clue that it's an endothermic reaction. For an air conditioner, it's making its surroundings feel colder, which means it's absorbing heat. So making its surroundings feel colder is a clue that it's an endothermic reaction. And then here our roasted pig picture for number 3. Anytime you're cooking something, energy is going into whatever's being cooked in order to cook it. So cooking, roasting, any of those types of things are clues that an endothermic reaction is happening. Now, sometimes students can get this confused because you think of cooking, you think you need flame or heat to cook, and that makes it feels warm to us as we're cooking. But you have to think about what is actually being cooked. The pig is the system here, and energy needs to go into the pig in order for it to cook, which makes it an endothermic reaction. So what I'd like you to do right now is pause this video and go to Google Classroom. I have a YouTube video posted of an heat flow animation. So it gives some good explanations of endo and exothermic reactions and gives you some visuals to look at. So once you've watched that video, come back here. So now that we've learned the difference between endothermic and exothermic reactions, we're going to draw and describe the energy flow in heat in terms of systems and surroundings, depending on whether we're dealing with an exothermic or an endothermic reaction. So when we're talking about endothermic and exothermic reactions, we're looking at energy as the flow of heat. To discuss the flow of heat, there needs to be two separate objects. Whether we're dealing with endothermic reactions and heat is flowing in, or exothermic reactions and heat is flowing out, we need to determine what heat is flowing in or out of. So the system will be the area of focus, usually the reactants and the products in a chemical reaction. The surroundings are everything else in the universe other than the system. So when you have a reaction that's going on in a beaker, this is your system, the actual reactants and products that are being formed. Everything else is your surroundings. So it's important to understand that heat will always flow from the hotter object to the colder object. So objects do not become cold, they simply lose their heat. So our examples here, we want to describe the heat flow when you put your hand into an oven at 375 degrees Fahrenheit. So the oven is warmer than your hand. So if you have your hand in the oven, heat will flow from the oven into your hand and make your hand feel warmer. The second example says describe the heat flow when you put your hand into a freezer at 32 degrees Fahrenheit. So what would actually be happening here is your hand has more heat than the freezer. So even though it feels cold when you put your hand in the freezer, that is because heat is flowing from your hand into the freezer where it is colder. Okay, so now we're going to learn how to draw an energy flow diagram. So the reaction we're dealing with is photosynthesis, and you first need to determine whether this is an endothermic or an exothermic reaction. We know from earlier that growing, anytime something is growing, is an endothermic reaction. So when a plant performs photosynthesis, it is growing, and that is an endothermic reaction. So the system needs to be labeled. The system is our plant. And then surroundings could be the air, soil. If it's a potted plant, it could be the pot around the plant, everything around the plant that is not the plant. And since this is an endothermic reaction, energy is flowing into the system from the surroundings. So you need to draw arrows showing the energy transfer into the system from the surroundings. And that's how you draw an energy flow diagram. So let's do a couple more examples. Our next example is baking bread. Remember, anytime we're cooking something, that's a clue that it is an endothermic reaction. Right, so the bread is our system, and the oven or the pan that the bread is in would be our surroundings. So in order for the bread to cook, energy needs to flow into the bread from the oven, so you should have arrows flowing into the system from the surroundings. Our next reaction is making ice cubes. So this would be taking liquid water and putting it in the freezer to make ice cubes. So in order for that to happen, energy needs to leave the water to turn it into ice. So that would be an exothermic reaction. So our water, or the ice cubes, is our system. The freezer is the surroundings. And then you need to have arrows showing that the energy or heat is flowing out of the water into the surroundings to form the ice cubes. Okay, and our last example is fireworks exploding. Remember, a big clue for exothermic reactions is fire or exploding, so when we see that, that tells us that this is an exothermic reaction. So our fireworks are the system, and then the air around the fireworks would be the surroundings. So fireworks take energy from the system and put it out into its surroundings. So you should have arrows going out. So now that you have learned about endothermic and exothermic reactions and how to draw energy flow diagrams, you're going to do some practice. Let me know if you need help.